to cover all the circuit one things for you guys for the first 2 weeks, which you don't like. But I think you guys learn a lot. Did you?
I don't know what you guys are talking about.
As a freshman.
Yes.
All right. So first thing I didn't cover last time was parasitic capacitors of the C5 technology. Did I spell this right? Parasitic capacitors. Okay, if we look at the cross-sectional view of the C5 technology, what C5 stands for? The 500 nanometer technology, right? Of the CMOS. What CMOS stands for? The complementary metal. So do you remember MOSFET? What is MOSFET? Yeah, metal oxide semiconductor field effective transistor, right? MOSFETs. So these are the fundamental components in all the, I think, the circuits in the modern devices, like the smartphones and laptops, right? So these are the transistors being used to form all the logic gates in your circuits, in the device, modern devices. So CMOS stands for complementary MOS. So MOS is the same MOS here, right? So CMOS is complementary MOS. Why complementary? So you got two types of MOSFETs. What are they? PMOS and NMOS, right? From Dr. Jessing, all right? So you should pronounce this as MOS, not MOS.
No, it's the other way around.
Really? No, I think he said it's MOS. I know in American English we pronounce it MOS, right? MOSFET.
Wait, no.
Yeah.
MOSFET. No, MOSFET.
MOSFET, right? So NMOS or PMOS, not MOS.
Yeah.
Yeah. In electrical engineering, right? So P is P-type. N is N-type, right? There are just two types of MOSFETs. The reason we have to call it complementary MOS because in the old days there's only NMOS to form the logic gates. And how do we do that? Remember Mr. Bill Mensch? So the first 6502 transistor, CPU, was built in NMOS logic because there's no PMOS at all. So it's not a CMOS technology, it's NMOS technology back into 1970s. How do you form a logic for just using NMOSes? Like here's VDD. Here's a switch, right? Could you form a logic from this?
Yeah.
Yes, still. If you turn on the NMOS here, what's the V out here? No, if you turn it on, this is 10K, okay? So what's the name? I'm just repeating myself for the whole semester that you guys will understand this. Remember this for the interviews, right? So why I put up 10K here instead of like 1K or 100? What's the name of the resistor? Let's just make it simple. What's the name? No, what's the name of the resistor? Yeah, pull-up resistor, right? Why is pull-up resistor? It pulls this point up to VDD. Even though there's not a behavior like just pulling it up, it's just pulling up the voltage to VDD. Makes sense? All right, so that's why you need a higher resistance instead of lower, because higher resistance means a heavy load or light load. Light load, right? If you have 100 ohms, it's a heavy load. It draws a lot of current from the VDD. Okay, so if you turn on the gate, of the NMOS, it's gonna connect at this point to where? If you turn on the NMOS, when you are looking at the NMOS, you are looking at the VGS, which is a gate to source voltage. And there's a threshold voltage for NMOS in the 1 micron technology, which is 0.8 volts. Okay, so if you turn it on, which means you'll turn on the channel, right? If you turn on the channel, this point will be shorted to where? Yeah. Then what's the voltage here? Yeah. Okay, so if you turn it on, you got a 0 volts, right? If you turn it off, this point will be what? No, sounds like electrical engineer, right? So if you turn it off, this point will be, no, will be, yes, but will be, yeah, to where? Yeah, will be put up to VDD. So you can toggle this pin by toggling this guy here. So you can still form a logic, right? But they use NMOS logic only. But whenever you compare the NMOS logic with the PMOS with the CMOS logic, what's the disadvantage by using just the NMOSes? Yeah, why? It's the resistors, right? Remember the NMOS resistors? So that if you just have a little transistor, you can make it super tiny. So what's the smallest one available on the market right now? Yeah, 5. In iPhone like 14, I believe it's 5 nanometer technology. So to form a 10K, you just did a lab last week, right? So to form a 10K resistor using NWL, it has to be pretty big compared to the 5 nanometer technology. So you can reduce the footprint of the chip. So that's why you can have your super powerful CPU put on the phone and eventually put in a pocket instead of the size of the entire room. Yeah. Okay, so we are drawing the cross-sectional view of the C5 technology, the CMOS technology, and now we're just looking at all the layers. Again, this is a cross-sectional view of all the layers. What's the first layer you can have? Yeah, Fox. What's the name of Fox? Fused oxide. Okay, and what's the name of this layer here? P-sub is a P substrate. It's a P-type semiconductor material. It's just a wafer. Whenever you see a silicon wafer and build the IC chips on the wafer, so that's just the wafer itself. That's a P-sub, the P-type substrate. And then you start building integrated circuits on the top. So the first layer is Fox, which is the fused oxide, and the second layer becomes what? The polysilicons, right? And you want to form, if you want to make a capacitor, so the first choice is using the 2 polysilicon layers. And first you got one here. That's poly what? Poly 1, right? And then you got poly 2. What's the effective area for the capacitor? And definitely you need vias to connect to where? So what's this layer for? Metal 1. And you need a little metal here, right? And here's a via. And you need another via, drill a hole to the top layer and get a metal 1. So these are the 2 terminals. So you saw the capacitors or resistors in the labs, like a capacitor like that or resistor like that. It has 2 terminals for each of them, right? So if you fabricate a capacitor in the CMOS technology, so the wires are going up. So this is a nanometer level capacitor being built into the IC chip, and you have the wires going up. So this is poly 2, this is poly 1, and the effective area for the capacitor is only this part of the polys, right? Poly layers. So what I want to talk about is the parasitic capacitors, because I can draw these parasitics for you guys first. For poly 1, yes, it is forming a capacitor over here, but however, there are parasitics, which is not a desired capacitor, but exists in the circuit. So this is poly 1 to what? Poly 1 to sub parasitic. Okay, and if there's a, you got metal 1, if I make this longer, and there's another parasitic, it's called metal 1 to substrate. Yeah, P sub, parasitic. And what's the layer here on the top? That's metal 2, right? And if you got a metal 2, and it forms parasitics between metal 1 and metal 2 as well. So during the layout, that's why a lot of times when we are laying out traces, if you lay out the metal 1 here, okay, do you think it's a good design to directly lay out another layer of metal 2 on the top like that to overlap them in order to save space? Are we actually saving space on the layout? No, there are different layers. It's not doing anything. So is this recommended? No, why? It forms a huge what? parasitic capacitor. You got a metal 2, metal 1, right? It's a cap. So if you are using a very low speed circuit, it probably doesn't matter because for the caps pass what? High or low frequency? High. Okay, if you have a high frequency, high speed circuit, this matters. If you have super low speed circuit, it's okay. It's not a good design. Okay, just keep in mind. So you should know that, you should be aware of that. There are all these sort of parasitics in your design. So if you can avoid that kind of overlap, just avoid it. Otherwise, it's gonna reduce the bandwidth of the circuit.
So the parasitic capacitors aren't intentionally put in there,
They exist. Yeah. So for example, there's another, from one of the projects we are doing, from Kelvin's project. Okay, Kelvin Reese. Yeah, for example, is probing temperature from the hot tubs in Puget Springs, right? And so the digital sensor, you want to convert the temperature data into digital as soon as possible because analog signal will introduce noises, right? So that's why you want that digital sensor, temperature sensor, just directly, inside the tub, hot tub, okay? And then the signal is being converted into digital signal. So digital signal is just 0 and 1s, right? Okay, and because it's using I2C protocol, it's somewhere around 10 kHz. It's not very high. But however, if you have a super long cable, so for example, they don't have a power supply just nearby that hot tub, because they have to make a super long cable from the hot tub and connect it to wherever. They have a little house to host all these power supplies and circuits. So in that case, what's the solution for that? I mean, if you use a regular cord, to communicate, just to send that digital signal from the sensor to the microcontroller in that little house, it probably won't be able to transmit that long. So if you have a huge cap along the cable, what's happening for the digital signal? So this is a cable, right? It's very long. It has parasitics everywhere. Okay. So if you are trying to transmit, so 10 kHz is not really high. I think it's probably higher than that, maybe 100K, I forgot. Anyway, so it's not very high, but if you have a super long data transmission cable, then you are getting a lot of parasitic capacitance. So it's trying to charge and discharge all these parasitics very fast, which means it's gonna do what for the digital signal? Yeah, it's gonna attenuate, right? Remember, it's gonna attenuate because it's charging and discharging. It won't be able to charge and discharge all these huge caps rapidly. So it's gonna slow down the signal, and eventually, if it's not able to charge up to over the threshold voltage, it will show all zeros eventually. So there's a special cable called the Ethernet cable. Spells it correctly. It's just all these internet cables, the blue cables you have seen in real life, and so these ones can be very long, right? Sometimes if you visit the IT office, you can see super long internet cables. So these cables are a little bit special. So they engineered it to make it a lower parasitic capacitance over there, but still you can not have a 1K, 1 kilometer long. It's still going to attenuate the signal a lot. But what I have researched online, the result shows for 100 kHz, for example, somewhere around 100 meters is still fine, which is good enough for that their property. So they probably have signal boosters. It's not difficult to. Oh, these are optical cables, right? Are they electrical cables? Yeah, maybe fiber optic, not electrical. Yeah, for long distance transmission, they need a super high voltage because it's going to attenuate along the line. So you need to boost it to like tens of thousands of volts in order to send that signal over and then regulate it to lower voltages for long distance transmission. Okay, so that's the purpose here. Just let you guys know there are parasitics. The second thing I have to cover is, let's see, important. You want to do homework assignments, you have to understand this first. So let's go back to the website. Couple things you need to know. So first, the homework 3 is due next Monday, right? Keep in mind, don't miss it. So you are good for all these questions until here. Okay, this is something you haven't learned that much. I'm going to draw one of the examples for you. And another one is this one. Can polysilicon wire be used as resistors? How to reduce the resistance of a polysilicon wire? Okay, let's show you. So first question, can you use polysilicon layer as a resistor? Yes. Is it lower resistivity compared to NWELs or higher? Lower. But if you want to use, it's rare, if you want to use polysilicon layer as a wire, to reduce the resistance, you can deposit a layer on the top. It's called silicide. Usually it's a metal material, tungsten. So this can reduce the resistance of the poly layer a lot. If you need more metal layers, but for C5, you only have how many metal layers in there? 3, right? You need more. You have a highly integrated circuit, you need more metal layers. This is probably the choice. You can coat a layer on the polysilicon, use it as a wire. Okay, this is the answer to that question. And then let's look at the layers. So for example, this one. So that's the top view of a circuit layout. Okay. How do you draw the cross-sectional view of it? I won't show you the entire solution here, but it's part of it, probably. Here's the substrate, right? If you cut from here, like a pie, right? Apple pie, you cut from here and look from the side. Here's what you look from the side, how it looks like. You can start from the bottom, so it's bottom top method, right? So what's the first, Fox, wait. No. Yeah, there's NWEL, right? So this is the size of NWEL. So the NWEL is embedded into the substrate. Anything else? Do you have the Fox across the entire wafer? No, why? It opens it up, right? Yeah. You have to open it up in order to dope that N-type material into the wafer. Then what's next? Do you have poly? Look at, wait, where is poly? You don't have poly. Then it's just metal 1, metal 2, right? See, metal 1, metal 2. It's just an example. It's not a circuit. It's still a layer, but it just don't have anything on it. No, if you don't have this poly drawing in the circuit, it doesn't exist. It still have that layer, but it just doesn't dope anything to the layer in the process, in the foundry. Just don't do anything because it's all blocked from the mask. So the poly layer doesn't have anything, right? What's next? Metal 1. So metal 1 has something. Where's metal 1? Here, right? That's the length of metal 1. And how do you want to draw it? You know how to draw it, right? I don't want to show the solution here. Do you?
Is it any different from the cross-sectional metal one that we've been drawing like previously?
Just, you guys are spoiled. I have to draw everything for you guys. All right. What about metal 2? Here, right? Anything else? Where? Anything else? Where? Yeah, how to draw the vias. Yeah. Okay, you'll do it yourself. Okay.
Didn't it go from metal all the way down to the metal? Or?
Why? It's a metal 1 to metal 2 via. Yeah. And you don't have anything else in here. There's no reason that you want to draw a super deep via to connect the two, right? You don't have. Do you have anything else? You don't have an unwell, but is the unwell doing anything? No. So this is something only exists on the textbook. Draw 2 vias here, right? 2 vias, and that's it. For this one, what about this one? Yeah, way more complicated, and there are 2. Just don't forget about that. I cut 2 lines, 1 here, 1 here. You need to do 2 of them. One quick question. What is this part here? And well, yeah, it is the body of the PMOS. I'm going to introduce that pretty soon. It is the body. You get the right answer accidentally, I know. By chance. We haven't covered that yet, but anyway, so unwell is the body of the PMOS. Okay, I'm going to explain that later. So you see 2 squares, 2 boxes, a bigger one, a smaller one. So the bigger one is called what? P what? P select. And the smaller one is called what? No, it's a PMOS. It's a PMOS. P active. Right? See P select. You need the.
You have P select, and then outside of P select, you have P active.
Yeah.
And you have the entire end.
Yes. Yes.
The P active is in the P select.
It is. Yeah. Yeah, that's true. Good memory from last time. See, let's draw it really quick. All right. So why do we have a? So this is one of the questions on the homework. Keep in mind, you need to understand that. Okay. So now here's a Fox, right? And we're doping. We're going to dope p-type material to the substrate. Okay. And here's a window. There's a window opens up the Fox. So this should be exactly the size over here. This opens it up. That's why it's the same size, right? So the P select is a slightly larger than that to avoid the alignment issue. So it's gonna dope p-type material to the Fox a little bit, but doesn't matter. Okay, that's why you see here P select is larger than P active for that purpose, right?
When we draw the cross section, we're only drawing the active section.
Yeah. Yes. Yeah. So how to draw it? How to draw this one? How would you draw it? All right, let's start from this one. And you are going to do this one. Let me see what you have here. You got a metal. This is poly. This is via. This is metal one. This is easy. This part is easy. Let's just do this one, okay? And now you draw a substrate. Okay, we're drawing this cross-sectional view here, right? Okay, what's the first one you want to draw? N-well. Here's N-well. And here's the Fox, right? What's next? Do I have poly? So you know the next layer is going to be poly, right? Wait, is that correct? What about the P plus? Yeah, go down to N-well. So where is the P plus? Look at the P active, the size of the P active. Okay. Do you have anything else over here? That's it, right? N-well and P plus. What's next? Do I have a poly? Yeah. Do I have metal 1? Do I have metal 1?
Yeah.
Yeah. Metal 1, so because this line crosses the two metal 1 pieces, right? So you have metal 1 here, right, from here to here. And then what? What else I'm missing? VS to where?
P plus to metal 1.
Yeah, do you have metal 1 to P plus? Yes, you do. Why? Yeah, for example, the NMOS, right? Okay, you got wires connected to these terminals to form the transistors. Definitely you have metal. You have vias for that one. So the via is gonna drill a hole to here and here. Make the connection to the PMOS, the P plus. Just shows you the solution for everything. I won't scan this. I won't upload this video. I'm just delete it. Select that frame and delete it. You know, that's why I have nobody visit my office during office hours, because all the videos are over there. Whenever they are doing their homework assignments, just watching the videos. All right, one more thing for PMOS. Okay, just round it up. We haven't covered that yet. It's important. What's the name of the PMOS transistors again? P-type MOSFET. Okay. Here's a substrate. Here's the gate. P plus. P plus. Here's a P sub, right? And I put a P plus here. The P sub is shorted to ground. Then what's going to happen? Yeah, all the two terminals are shorted to P sub. That's why you put the P plus in where? Yeah. Okay, so the body of the PMOS is N-well. The body of the NMOS is? It's a long week. It's Friday night, Friday afternoon, I understand that. So the body of the PMOS is N-well, the body of the NMOS is P sub. Okay. So you need a what? You need a P, you need an N-word here as a body contact, right? You need a terminal here. What's the name of the terminal? It's just N plus, right? Why do you need that? Do you need to ground the N-well, or you want to tie it to somewhere else? It's a PMOS, keep in mind. If you look at the inverter circuit, short the two gates. Here's the body. That's how you do it. So the body of the PMOS is shorted to where? To the voltage? To what voltage? Yeah, so let's see how this works first. Okay, source, drain, and in order to turn on that PMOS, you need to generate a potential drop across S and G. So this is the source, this is the gate. So VSG should be greater than VTHP. So for the 1 micron technology, VTHP is 0.9 volts. Okay. I open it up. How that works? See the voltage potential compared to the source. The voltage potential at the gate is negative or positive? Negative. So it's going to attract what? The channel. Holes. And then you connect the source to a positive voltage. It's going to pump these holes to where? From where to where? Yeah, so the current is going to flow like that, right? It's like a PMOS transistor. You want to turn it on, you have to add a voltage here. It's called VSG. Compared to NMOS, you are connecting a voltage here, ground. This is called VGS. So VGS must be greater than VTHN, and for PMOS, VSG must be greater than 0.9, which is VTHP, in order to get a current flow that way. That's how I turn it on. Just keep in mind. Because the holes has a lower mobility compared to electrons. It takes more effort to excite them. Right. Yes. Positive charges.
So they always move to the direction of the field.
Yes.
Why are they positive though? I've never understood this.
Because they are not negative. Because the holes lost electrons, and electrons take.
Why is it suddenly turn into a positive?
It's so.
I don't know.
So again, holes are not moving. Holes are not moving. Electrons are moving. But in order to understand this better, in a better way, so we consider holes are moving. But actually, it's the electrons are moving the opposite way. Holes are not moving. Holes are just spots in the crystal.
Yeah.
Yeah, they're not moving. What is moving the electrons? Electrons moving that way. So it's just a Joule vector for the movement of the holes. It's moving that way, relatively.
Okay, but why do we denote the holes as positive then?
Because it is something lost negative charges and it becomes positive charged.
Oh, okay.
Yeah.
Yeah. It's just quantum mechanics.
Any three understands what a hole is.
Yeah.
I don't know when they keep moving around like that.
They're not moving. I just said they're not moving. Electrons are moving. But I just drew the arrow here. If you consider that they are moving, then it's just easier for all the calculations for the Ohm's law. Right? They're not moving. The electrons are moving the opposite way. Okay. So if the voltage, so here, because the body of the N well is N plus, again. Okay, so that's the body of the N well. Why? Why, if I put I dope a N plus material into the N well, then this becomes the body? Why? Remember, why do we have NMOS and we are not grounding the bottom of the wafer, right? We are doping a P plus here and ground this guy in order to ground the substrate. Because they're shorted, they're both P type. So they're shorted together. Right. Oh, is that?
I thought you drew N type.
So the N well right now becomes the body of the PMOS. So N well becomes the body of the PMOS right now. So that's why I need a N plus in here as a body. If I want to short the whole N well to somewhere, I need to have a little N plus here to short that one somewhere. Otherwise, how do you short it to somewhere? It's just a material in the wafer. How to short it to somewhere? You need a contact. Okay, that's why you put N plus here and short it to the highest potential in the circuit to avoid body effect. Y to avoid what? Body effect.
Do we go with body effect?
Yes. So if you look at the so what's the potential over here in to how to model the body effect? Remember? So for the animals, what are being attracted to the channel here? Electrons, right? So this is S, this is body, which is B. If this one, the source and B has a potential difference, okay, then this voltage, positive voltage here, is going to attract some of the electrons. So it's going to lose electrons in the channel. So it's going to require more effort here to turn it on. Okay, so to increase VT, so this increases VTHN. That's how the body effect works here for the NMOS. What about PMOS? What about PMOS? So the best way to avoid that body effect is just short S to B. If you look at NMOS here, here's B, right? Here's the body, here's source. Did I short B to S? Did I short B to S? Yes. So that's how you avoid body effect. And for the PMOS, you short the body to VDD. And now let's look at the PMOS here. And I think the body effect for PMOS is if you have a voltage potential drop between, here's B, right? Between B and S, VBS. If VBS is larger than 0, then there will be a body effect for the PMOS. And let's think about why. Remember here, this anode attracts electrons, so it loses electrons. But for PMOS, it attracts holes. So the gate voltage attracts holes in order to make a channel, right? However, if you have a voltage drop from B to S, which means you got a cathode here, which will attract what? Yeah, holes to where? To this voltage. Then what's going to happen? So the channel loses holes. It takes more effort to inverse that channel from the gate voltage, which will increase what? Increase VTHP. So there will be body effect. And if you don't believe that, let's do a simulation here. Look at it. So I'm also showing you guys how to use, since we have been doing, I guess, we've been using NMOS, but now let's run a PMOS example. So let's grab a PMOS. You want to use PMOS 4, I guess, right? And since I'm recording, you can refer to this video later. So just let you guys know, in LT Spice, it uses, so whatever node here is closer. So this is a gate, right? So the gate is always closer to the source, even though sometimes interchangeable, but just consider that this is closer to the gate, that's why this is source. But for the PMOS drawing, whenever you are drawing CMOS, you put a source on the top for PMOS. Here's source, you have to label it, source, drain, source. Okay, let's go back to the simulation. So now how do we rotate it? Grab a little hand tool here, do this, and rotate. Still doesn't look really right, and mirror it. Directly pull up and mirror it. Okay, so now you got a nice looking PMOS. And how to change the parameters? Right, if I put a 2U, 2 micron, and 20 micron. It doesn't actually matter that much. It's not showing up. So you want to show it up, you want to do Control right click, and check this box to show, to display that dimension of the PMOS transistor. And do you like this name, PMOS, for the model file? We are doing a 1 micron technology, by the way. What's the name you want to use? P_1U. Yeah. Okay. And then let's grab a voltage. How many voltages do we need? Probably need a 3. Since we need a body effect voltage as well. Okay. And then remember, it's a VSG. In PMOS, keep in mind, you need a VSG to turn on that transistor. So that's why I'm gonna draw a voltage drop from S to G, right? The voltage source is voltage source. It's gonna do whatever you ask it to do. Keep in mind. So if you want to drop the voltage from source to gate, for like, it doesn't matter because we are going to do a DC sweep. Let's just put a 5 volts here. It's way larger than 0.9 volts, which is the threshold voltage, right? And then what? I want to give a potential from S to D in order to drive the hose from top to bottom, right? Let's move this one. All right, I'm not going to modify the VSD here because I'm doing a DC sweep for VSG. So I just give a 5 volts here. 5 volts, no problem. And I'm going to rename this guy like VSG. Then if you are running a simulation as in a correct way, in a normal way, you want to tie the body of the PMOS to where? VDD. You want to do that, right? However, what we are doing is generating a VBS to make a what? Body effect, right? I'm gonna rotate. So it's VBS. Remember, on the top of the PMOS is source, bottom is drain. So you want to name, you want to give a it's a variable, right? VBS. You can pick it up. Wait. It's a P. Now let's write, what else I'm missing? Yeah, if you don't have ground, it won't simulate. Don't forget about that. Then the SPICE code. What's the first one? Just include that model file, right? And then Control Enter, keep in mind. You have multiple lines, Control Enter. I'm running a DC sweep. I want to see if the body effect is going to affect the threshold voltage. So I'll do a .dc for which one? For which voltage? What's the x-axis here? No, VBS, yes, because I want to, wait. No, I want to change the VBS to see if I have different threshold voltage. But still, you are looking at the IV curves. So the x-axis is what? VSG, the VGS, right? Remember, after a threshold voltage. So I'm just drawing one for NMOS, VGS, ID. Remember, after it passes the threshold voltage, the current goes up. And here's 0.8 volts for NMOS. If you have a different threshold voltages, you are seeing this. This is what you expect. Okay, let's come back here. So I'm doing a DC sweep for VSG, and from 0 to 5 volts, right? Control Enter. and it's dot. It's so boring. He got bored. Oh, you are focused?
Yeah.
Great. All right, let's see what's the specs called for parameters. So it's dot stat function, right? Dot stat parameters and the parameter and list, okay? Dot what? Dot stat, right? Hmm? Oh, so you are focused. Dot stat param, right? Param what? Which parameter you are? Yeah, VBS and list, right? So what are the three? We just tried three different voltages. For example, 1, 2, 3 volts. Because there are the three voltages I'm gonna try. And for the DC sweep here, it's 0 to 5 volts. They're not the two numbers DC, it's a continuous range values. And then here, is this anything we need? Everything we need? Yeah? Let's run it. So we're gonna probe ID, right? How to fix it? It's entry-level way. Entry-level solution. Is there a better solution to it? Is there a better solution to it to make you more professional or something? Wait, so what's happening? So when I probe the current here, it's actually plotting the current getting to the point, not exiting the point, right? So that's why it's negative. How do you plot it the other way? But the LT-Spice is not automatically doing that for you. Call, no. Let me show you a way to do it. Put a resistor here. You are saying, hey, you are changing the circuit. Why? I mean, very close, but not 0, but 0.01. What about that? So remember, I think in the first lab, or I forgot which one, we were able, so the resistors has polarities in LT-Spice, remember? So they recognize the different nodes. So if you rotate it, you can inverse that current direction. So if we do this, and we plot the current direction, if it's wrong, we are going to rotate it and make it right. You know what I mean? Now it works. And now let's see if this is correct. So we have blue, red, and green. Blue, red, and green, 3 colors. I'm going to verify if these are the 3 values we have, right? 1, 2, 3. And if you go to control panel and waveforms, color scheme, see V1 is the first value. V2, black is the first value, blue is the second value, red is the third value, and then the greenish color is the fourth one. So we know that the order for the colors for different voltages are blue, red, and green. I know it's not green. What's the name of the color? I don't know.
Yeah, this is all.
Yeah. So you know that whenever VBS is 1 volt, it's last body effect. So you are still having a pretty good threshold voltage. But whenever you get a big VBS, the threshold voltage is increasing because it turns on the transistor a lot later than the first one. That's how I'll verify it. Make sense? Let's see. Oh yeah, it's from like 0.9 volts to 1 point. I don't know. Anyway, it's bad. Okay. Mm. All right, let me see if there's something else I need to cover. There's one thing you need to know for homework 4. And this one is due, no, you should be able to do it. No, you are still not. It's due next Friday though. I wouldn't rush for anything. There's a lot of series behind it. Any questions do you have for whatever we covered today?
So for using polysilicon wires as resistors,
No, no. As a resistor, no. You can. Just don't put any silicide on it. If you use that resistor, I put the 2 questions in the same problem, which will confuse people. But if you know what you're doing, so for the polysilicon layer, you can use it as a resistor material, yes. If you want to use it for the different purposes, like just a conductor, you need to put silicide on it to reduce the resistance, but not being used as a resistor anymore. I think it's all the same process. You shouldn't be able to do anything. Yeah. All the time.
Use the holes, but you know what? I'll have absolutely.
well, we're gonna talk about it.
Yeah, we'll talk
Okay.
about that.
Okay. Yeah. So I put this homework 4 on Friday, but you are still not really ready for it. So I'm gonna introduce more on Monday. Okay, so don't rush for it. I know you haven't started homework 3 yet because it's due next Monday. You'll start working on Sunday. That's what I know. But anyway, just let you know, if you start this early, you will see a lot of problems.
Actually, I have a question about the third question.
Yeah, the capacity.
Oh, which one?
I haven't talked about it.
Yeah, we can. Yeah, which one? Still have 2 minutes, 1 minute.
What? The diode capacity.
Which one?
3. Okay.
Oh, one's, oh, this one.
Yeah.
It remembers it's all in the video. I recorded. 4 bias is going to be thinner, and then you get larger. A Y is getting thinner, so it's attracting electrons from the depletion region back to the source. Yeah. So it's getting
So
thinner.
it's the same for the diode capacity.
The capacitance gets bigger as your plates get closer.
Yeah.
That makes a lot of sense.
Yeah. All right, let's call it today. Thanks for coming, Dr. Charlie.
Thank you.
Yeah.
Appreciate it.